Hello students, let's talk about potential energy curves. So as you know, the potential energy of an object depends on where it is, such as let's say you're pushing on a spring, and as your hand squeezes the spring, the potential energy of the system, the spring plus your hand I guess, increases. And so that's what this is graphing. This side here represents the spring getting compressed. The other side here represents the spring getting stretched, although actually it could be turned around. It doesn't have to be that way. And so this is a parabola. It's 1/2 kx squared. And to get some numbers, easy numbers to deal with, I made k equal to 1. So let's take a look at the slope of this curve. In calculus, it's called the derivative of the curve. So when x is bigger than 0, it's curving upward. And this area here, it's got positive slope. This is an area where the force, in this case a spring, is pushing to the left. Okay, now let me point out something. Let's suppose that you put a little marble right here, or a ball. It would roll to the left because there's a component of force the gravity force has a component that's to the left. Okay, so just keep that in mind. Now, if we talk about the left side here, the curve is sloping downward. And if I were to put a ball here, it would feel like a force to the right. Okay. So the reason I'm bringing up the ball idea is that what the bottom line is that the slope of a graph of potential energy tells you the force on a particle, on your hand, or on an dry ice puck pushing up against a spring. It tells you what the force is on the object that's interacting with this potential energy. Okay, so here let's work a little bit more on this relationship between the force and the potential energy. So this is what's happening here is what was happening in the parabolic curve that we just looked at. So we start out here at the center of the curve at x equals 0, and the spring is relaxed and the force is 0. And then we push to the right, and the spring pushes back to the left, right? The springs, you're pushing to the right, but the spring's reaction force is to the left. Now, as you squeeze and squeeze the spring, its potential energy is going up, or the system's potential energy is going up as 1/2 kx squared. So, yeah. So if I make a graph of both of these things, so here I'm graphing f equals minus kx. And then here I'm graphing 1/2 kx squared. And this graph here is the negative of the slope of this graph here. So if you're taking calculus, what we would say is that this graph here is the negative of the derivative of the potential energy graph. And another way of looking at this is that if you wanted to figure out this curve here from that, you could do it by finding the area between the x-axis and the force curve, finding this area here. Now, finding the area in calculus is called taking the integral, and this is an integral sign right here. So If you don't want to think about calculus, it's the negative of the area between the x-axis and this force line or force curve. If you do want to think about it in terms of integrals of calculus, then it's the negative of the integral of f of x dx. Okay? So there we go. Looking at it in a little more detail. So let's, sometimes this is hard to remember, right? Because, especially with the negative sign. Somehow that causes a little bit of confusion. And so let's think about it this way with this trick. So let's suppose that I had a roller coaster shaped potential energy curve. So when you're up high, there's more potential energy. When you're down low, there's less potential energy. Let's say this was a roller coaster. Well, which way would the roller coaster car tend to go right here? Oh, it would tend to go to the right. And oh, that matches up with the fact that the slope is downward. All right. So now that I think you understand this, right? It's not that tricky. Let's look at this graph and fill in this this little chart here. So at location A, what would be the slope? Is it a positive slope or a negative slope? So, well, its slope at A up here, it's sloping upward. But remember, the force is the negative of the slope. So that means the force must be negative. And that means the force is to the left, right? Which makes sense, right? If you put the roller coaster cart right here, it would tend to roll to the left. We'll get to this in a minute. All right. Now let's take a look at B. What is the slope right here? Okay, I didn't do a very good drawing, but let's say that we're right at the very top. At that place, the slope is 0. Now the force is the negative of the slope, so it's 0. Okay, and the force is neither to the right or to the left, so it doesn't really matter. And now here we go. Is this a maximum of potential energy or a minimum, like right here? Well, okay, I gave you the answer. This is a maximum of potential energy. And coming back to the force, right? The force is 0. So that means we have equilibrium. However, there are two flavors of equilibrium. There's stable equilibrium and unstable equilibrium. And this one is unstable because if I put the cart, or here, it's easier to just draw a little ball. If I put a little ball up here, okay, it's not going to go anywhere, but if I give the tiniest push, it'll either roll to the right, or if I push to the left, it'll roll to the left. And so this is a unstable equilibrium point. Unstable. Okay. So C, I think we can, the answers to that one. D, all right, here at D, the slope is 0. Okay, D. So that means the force must be 0. So we don't really care here. And which one is it, a maximum or a minimum? Well, this is obviously a minimum of energy. And at a potential energy minimum, we have stable equilibrium. It's stable. All right. E, F. I think you can figure all of these things out. Let's do just yeah. Okay, you guys can figure the rest of this out on your own. All right. Let's move on. I put the answers. And I just I explained equilibrium, and I explained stable equilibrium, and I explained unstable equilibrium. Okie dokie. Okay, now coming back to this roller coaster thing, this could literally be the potential energy of a roller coaster, right? If the roller coaster car is up high, it'll have high potential energy, and okay, fine. This is a literal thing, and it works for that. I used it just as an analogy, as an explaining tool, but a real roller coaster really has a potential energy curve just like this. But what I want to do right now is point out something that relates more to the idea of a spring. Okay, in chemistry, we talk about molecules, and this explanation is going to use diatomic molecules because they're simple, but this also works for multi-atom molecules. It's just that they get more complicated. But anyway, if I were to graph the potential energy of two atoms in a simple molecule like nitrogen and 2, when the two atoms in the molecule get very close together, the nuclei start to repel each other. So the plus nucleus of one atom and the plus nucleus of the other atom push apart. And it's like a spring. It's like an electric spring, but you're compressing this electric spring, and the molecule's potential energy goes shooting up, right? Now, if you start pulling the two atoms apart, right? These are molecules. The interaction of the negative electrons and the positive nucleus of the other atom kind of wants to pull the two atoms together. So it's a spring in the pulling sense as well. The only thing is that the springs that we're used to have a parabolic U versus X curve, whereas the molecules don't have there's something that sort of looks a bit parabolic here. But when you get real close, this is more like a hyperbola, right? It shoots up to infinity, and then over here, this is I don't know. It kind of looks like an exponential, an e to the minus x sort of thing, and it eventually goes to 0. So molecules have their own special potential energy curve. Now, but what's cool is that you see here, if you can graph, and this is something that you can do with a combination of electricity theory and quantum mechanics, a little bit of quantum mechanics, and you can find that, yeah, the potential energy curve will be flat right here. This is a stable equilibrium point for the molecule, and sure enough, the molecule, if you measure the distance between the two molecules, it's going to be this distance here, which I've labeled x0. Okay. Now, when a atom is it's just sort of stuck here, right? If you just look at a cold nitrogen atom, it's something really cold, like close to absolute 0, the two atoms are just there, not really moving much. But if you warm up these nitrogen atoms, molecules, they're going to start to have more energy. And you're going to start to see them going boing, 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 boing. And it's sort of like having a marble. Let's say I have a marble here that goes voom, voom, voom. And if your molecule has this much energy, we call this an energy level, right? This amount of energy, then you're going to see that the two atoms are going to be close together, then they're going to be at their equilibrium place, but they're going to overshoot, then they're going to go be here, and they're going to do like this. They're going to bounce back and forth, just like a ball would roll back and forth. And so that's what molecules do. They bounce like that. So this way of looking at molecules is really powerful. Now, if you keep heating up the molecule, right, you add more energy, it's going to start, let's say it has this much energy, right? It's going to be doing this and this. And then you give it more energy, and it's now, messed up. It's going to have even more, right? It's going to be, and oh my God, it's almost breaking apart here. If it had just a little bit more energy, let's say we give it a little more energy. Okay, let's do that. We'll give it this much energy. So what'll happen is the molecules are going to start coming apart, and they're never going to come back together. You've put in so much energy that you've broken the molecule. In chemistry, we'd say you've disassociated the two atoms of the molecule. So looking at potential energy curves teaches you a lot about chemistry, about the energetics of molecules. All right, so I'm here. I've kind of gone and put in a lot of questions and answers, and I think this lecture is going to get to be a little too long, but I invite you to work your way through. I think you'd find it worthwhile. Now, I'm going to stop the video at this point, but we're going to come back and do some exercises that relate to this idea here. And I will be assigning these exercises. It's a worksheet, so make sure that you see the next video because I think you're going to need it to do the worksheets. Okay, see you later.